My name is David Layzell, and I'm the Energy Systems Architect with the Transition Accelerator. Thank you for joining us today for a webinar on hydrogen and the decarbonization of steel production in Canada. It is being presented by the Edmonton Region Hydrogen Hub, an alliance of organizations that include municipalities, the economic development organizations in the Edmonton region, academic affiliations, Indigenous communities in the region, as well as provincial governments and the federal government. The hub works together with industry partners and their associations to accelerate the development of a hydrogen economy in the region. And actually, to be honest, across Alberta and throughout Canada. Before we begin, I'd like to acknowledge that the Edmonton Hub is located on Treaty 6 territory, a traditional meeting grounds, gathering place, and traveling route for the Cree, the Saulteaux, Blackfoot, Métis, Dene, and Nakota Sioux peoples. We encourage everyone watching to reflect on the territories, the treaties, and the people where you live and work. This webinar is part of an ongoing webinar series from the Edmonton Region Hydrogen Hub to provide industry, government, and investors with the knowledge and tools so they can take advantage of the opportunities in the Edmonton region, throughout Alberta and across Canada, to produce low-cost, low-carbon hydrogen and use it to accelerate the transition to a net zero emission energy systems. As you can see past webinars on our website, and the website's erh2.ca, this presentation will be available tomorrow, so you'll be able to pass it on. So if you find it interesting, be sure to share it with others, some of your colleagues and other friends and neighbors, and you give it as a family gift very soon, maybe that, Christmas gift or something. For information and updates about future webinars, be sure to join the mailing list that's on the ERH2 website and follow the Edmonton Regional Hydrogen Hub on Twitter and LinkedIn. Now, we're very pleased today to have David Billedeau with us to moderate this webinar. David Billedeau is the Director of Climate and Environment at the Canadian Steel Producers Association. This is the organization that commissioned the Transition Accelerator through the work that you're going to be hearing about today. At the CSPA, David is focused on establishing synergies that will advance the steel sector's economic competitiveness and environmental performance targets. Prior to taking on that role, David served as a senior director at the Canadian Chamber of Commerce, and he was a government relations specialist at Toyota Canada and a policy advisor with the Government of Canada. In addition to his role with the Canadian Steel Producers Association, David is currently completing a PhD at the University of Waterloo, my old alma mater, I might add, but he's within the Faculty of an Environment, where he holds a research fellowship with the Energy Council of Canada. David, I'm passing it over to you. Thank you.
All right, Professor Layzell, thank you so much for the introduction. Welcome to today's webinar. Our topic, as previously noted, is on hydrogen and the decarbonization of steel production here in Canada. To convert iron ore into the iron required for steel making, the Canadian steel industry primarily relies on coal, on coke, and on natural gas in large blast furnaces. Currently responsible for approximately 2% of Canada's greenhouse gas emissions, the steel industry is committed to reaching net zero emissions by 2050, but reaching these goals will require innovative new approaches to steel production. For today's conversation, Professor Adnan Khan will share a recent report about the potential solution of using low-carbon hydrogen in the steel production process, looking at the economic, technical, and logistical challenges this approach would involve, and explore recommendations on policies and strategies to help shift the steel industry towards a sustainable future. Adnan is an assistant professor at the University of Alberta and the principal investigator for the Energy Transition Lab. He has over 10 years of industrial and academic experience leading research teams across the value chain of innovation, technology development, and commercialization. Adnan has played key roles in fostering collaboration among industry, government, and academia. And the goal of his research lab is to develop and analyze novel materials, technologies, and credible transition pathways towards net zero emissions for Canada. So throughout the presentation, please put your questions in the Q&A box, and we will get to them later on in the webinar. And please use the Q&A box only for questions rather than the chat box, as this helps us keep everything in one place. If you like someone's question, feel free to upvote it, and this will help us determine the order that questions will be addressed. Now, Adnan, over to you to get us rolling here, and thanks again, everyone, for joining the discussion today.
All right. Thank you so much, David, for the introduction. I will go ahead and share my screen. Work. Can you see my slides? All right. All right. Good morning, good afternoon, good evening to wherever you are. And thank you, David, for the introduction. My name is Mohammed Adnan Khan. I'm a professor at the University of Alberta. I'm also the principal investigator of the Energy Transition Lab there. And today, I'll be talking about a recently concluded study on hydrogen and its potential role in the decarbonization of steel production in Canada. Let me get my laser pointer out as well, and I will get straight into it. All right, so before I get into my talk, I need to acknowledge everyone involved in the study, the funding from Natural Resources Canada, the steering committee at CSPA, and all the authors and content creators at the Transition Accelerator and also at Thorn Associates. All right, so my presentation outline for today has 6 key sections. I'll start off with some general information on steelmaking in Canada, followed by the context of the study, and I'd really like to lay out the objectives of the study. Then we have steel production, energy use, and emissions. Then we'll really present all of the analysis we did around a case study of the use of hydrogen DRI in the Hamilton region. Then we will consider the steel industry as an anchor tenant for a larger hydrogen economy, and followed by some recommendations that came out at the end of the report. All right. So steel making in Canada and current decarbonization measures. So when we talk about steel, steel is really deep rooted in our society. We cannot function without steel. It's really part of our daily lives. We use steel in different sectors, such as construction, such as industry, health, transportation, and other sectors as well, right? It's really key part of how we function as a society. Now, Canada's steel sector is a $15 billion industry. We make around 13 million tons of steel products. We're among the top 20 steel producers in the world. And directly, indirectly, the Canadian steel sector employs over 100,000 people, more than that. So this is a rough number. What I have on a graph on the bottom here, you can see the steel production by different countries. Again, you can see Canada on the list, but quite obvious from the graph is there is one country that dominates global steel production, which is China, which makes more than 50% of global steel. Now, again, another important thing to highlight here is that steel will also be an integral ingredient for the energy transition, with solar panels, wind turbines, dams, electric vehicles, all depending on steel on varying degrees, right? So an integral piece of the energy transition. Okay. Now, when we talk about Canadian steel sector, the total emissions, like David was talking about, is about 2% of our country's GHG emissions, with about 15 million tons of CO2 annually. But what I need to really highlight here, since 1990, the Canadian steel industry has invested to reduce energy consumption and emissions, which has resulted in over 30% reduction in emissions by 2016. And this is one of the lowest GHG intensity globally for steelmaking. And the graphs here, what I have here is basically 2 types of steelmaking. We'll talk about it in a couple of slides. But what I have on top is integrated steelmaking. Again, you can see Canada is one of the lowest, if not the lowest, in terms of carbon intensity for integrated steelmaking. And also secondary steelmaking, which is through electric arc furnaces. Again, because of the low carbon electricity we have in several provinces available to us, we can really make secondary steel at with very low carbon intensities. Now, where do we produce steel in Canada? That's the first thing that comes to our mind. We basically have 3 integrated plants for primary steel production that uses the traditional route of blast furnace and basic oxygen furnace. I'll talk about it in a couple of slides. All 3 integrated plants are really located in Ontario, in southern Ontario. We have 7 electric arc furnaces for secondary steel making throughout Canada. And basically 72% of our steel making is concentrated in southern Ontario. We also have 1 DRI facility in Quebec, and DRI is really the core piece of our analysis here, and we'll talk about what DRI means in a slide. So what do we do? Where does Canadian steel go? In terms of our exports, Canada exports steel to across the world, to more than 130 countries and territories, but primarily most of our steel goes to the United States here, right? And that's some really setting the context, that's some information on Canadian steel sector and Canadian steel making. And in terms of decarbonization measures, key announcements by the Canadian steel sector are as follows. So there's a few key announcements that came out recently. One is that Algoma Steel has announced to transitioning from a blast furnace, a basic oxygen furnace route, to a full electric arc furnace by 2026, right? ArcelorMittal Dofasco plant has invested in a 2.5 million ton hydrogen-ready natural gas DRI furnace to replace the current integrated steel making. They've also tested in their DRI facility in Quebec, they have tested partial replacement of natural gas with hydrogen. So these are some key developments in this transition to net zero for the steel sector. But what I also need to highlight here when I talk about all of these announcements, that each organization's approach to decarbonization and pursuing carbon reduction technologies will be unique and depend on several factors. All right, so let me get straight into the study and really set the context of what the study was about. The study was in alignment with CSPA's vision to achieve net zero CO2 emissions by 2050. The study is also very important in the context of a slowly developing market for low GHG steel as different industries look to decarbonize. And like I said before as well, there are various options for decarbonizing steel production being investigated, and the likely path forward will be a combination of several solutions. And just in the previous slide, I highlighted that we had a recent announcement by ArcelorMittal Dofasco plant in Hamilton, which has committed to transition to natural gas DRI facility, which has the potential to be hydrogen ready in the future, right? So really the purpose of this report, and I'll take my time on this, is to explore the potential for hydrogen to decarbonize Canadian steel with a focus on possible sources of low GHG hydrogen and the cost it will take to deliver hydrogen at scale to the Dofasco plant. So it's really around the Dofasco plant that our study was centered around. I also need to highlight here for the audience that options beyond the adoption of hydrogen for steelmaking are not discussed in any depth in the report, but should be considered as an integral part in the steel sector's decarbonization strategy. So that's important to keep in mind. All right, so the next section is about energy use and emissions associated with Canadian steel production. Before I get into it, I have a slide here. It's quite a busy slide, but this is basically talking about various ways of steel making. So primary steel production, we've analyzed 3 different routes for making steel. The traditional route with the blast furnace, blast oxygen furnace, the natural gas DRI route, and the hydrogen DRI route, right? You can think about these 3 routes as three components, which is basically processing of raw materials right at the top here, iron making here, and then steel making at the bottom. So it really happens in 3 steps, right? In the traditional route, where you have your blast furnace and basic oxygen furnace, you would process your raw materials such as coal to make coke. Coke basically provides your energy source, but also is used as a reducing agent to reduce your iron ore to give your pig iron in this case, which is then further converted to steel in the basic oxygen furnace. The DRI routes, whether it's a natural gas DRI route or the hydrogen DRI route, typically use lower energy because the iron ore is reduced below its melting point. In the natural gas DRI route, we basically use natural gas, which is converted to carbon monoxide and hydrogen in the furnace, which is used as a reducing agent and also provide your energy source. And then further, the direct reduced iron can be converted to steel in an electric arc furnace. Hydrogen DRI, very similar to the natural gas DRI process, except now you have a carbon-free source of energy, which is hydrogen, and which is also used as your reducing agent, right? This process has the best potential for decarbonizing steel sector, which is well recognized around in the industry, but really only makes sense when you have low carbon hydrogen available for steel making. It could come from green hydrogen, it could come from blue hydrogen, and we'll talk about this in the presentation. And just 1 second. All right. So when we talk about energy use in primary steel production, we talk about the 3 different routes. What I have a graph here talking about energy demand. So we've summarized the energy demand from the 3 different routes that I showed in the previous slide, which is basically the blast furnace, basic oxygen furnace, which is a traditional route for integrated steel making, which is what we use in Canada, but also the natural gas DRI route and the hydrogen DRI route. I have 2 sets of data from this report or our analysis, and also data from another source, another reference here. There are 2 key points I'd like to highlight here. DRI route is more energy efficient than the blast furnace, the traditional route, which involves the blast furnace and the basic oxygen furnace. So DRI, like I said, because you're really reducing iron ore below its melting point, the energy requirements are lower than the traditional integrated steelmaking route, right? The DRI can be fueled with either natural gas and hydrogen. If you look at both sets of data, the hydrogen DRI route requires similar energy demand versus the natural gas DRI route. But then when we look at GHG emissions, and these are basically scope 1 direct emissions, compared to the traditional blast furnace, blast oxygen furnace route, on-site emissions could be significantly reduced by the transition to a DRI route. So when you transition to natural gas, you could potentially reduce emission by about 70%. If you add upstream emissions related to electricity generation, natural gas production, we're looking at emission reductions about 50 to 60%, right? But what is very clear from the chart here, that the hydrogen DRI route really has the best potential to reducing your scope 1 GHG emissions. Again, the entire process only makes sense when you have low carbon, very, very low carbon hydrogen available to you at scale to do this process. But another key thing I'd like to highlight here, and which is really the key message from this slide, the key takeaway message is this. Now, compare natural gas DRI versus hydrogen DRI. Let's talk about this transition, which is going to happen in the Dofasco plant, which is, which we're envisioning. Assuming a natural gas price today of $5.50 a gigajoule, and if at best case scenario, if you assume a hydrogen price at $2 to $4 a kg of hydrogen, which is basically about $14 to $28 a gigajoule. What straight away strikes you is the fuel energy price with this transition from natural gas DRI to hydrogen DRI will mean that your energy cost will be 2.5 to 5 times more with this transition to the hydrogen DRI. So the key message really here, the minimizing the cost of hydrogen supply will be critical. We need to build supply chains that can deliver very low cost hydrogen if we really have to make this economically viable. So when we talk about hydrogen supply chains, the first thing we have to talk about is hydrogen production. The slide I have here is an analysis that we do. We have very detailed models that we develop around green hydrogen production. So when we talk about water electrolysis to make hydrogen, what we know, it is very energy intensive. The electricity requirement is about 55 kilowatt hour of electricity, low carbon electricity to make 1 kg of hydrogen, right? So it really depends on the cost of your electricity that really drives the cost of hydrogen produced. So with current cost of electrolyzers, what I need to highlight here, there's a lot happening in this chart, but what I can highlight here is today, if you have to make low cost hydrogen via water electrolysis, let's say at $3 Canadian a kg of hydrogen, you will need access to low carbon electricity at a very low cost of $30 a megawatt hour, which is about 3 cents a kilowatt hour. But also equally important, you need that electricity available to you with very high capacity factors to really operate these electrolyzers for long operating hours, right? And that is very critical. With a forecasted decrease in the cost of these electrolyzers, we can afford slightly higher electricity prices in the future. But even in a situation where we have lower capital costs for electrolyzers in 2040, you will still require very high capacity factors of these electricity. and you can afford electricity cost of slightly higher, about 5 cents a kilowatt hour or 50 Canadian dollars a megawatt hour to make hydrogen at 3 Canadian dollars a kg. So that's about water electrolysis. So what about blue hydrogen now? So hydrogen can also be made by natural gas reforming, and that's how primarily we make all of our hydrogen in Canada, but also the rest of the world. And when we talk about natural gas reforming, you can do steam methane reforming, or you can do autothermal reforming. And when you couple these technologies with carbon capture and storage, you get blue hydrogen, right? And depending on the carbon capture rate will determine the carbon intensity of your hydrogen. What I have a graph here is basically showing you levelized cost of blue hydrogen production as a function of natural gas price. So basically, the cost of blue hydrogen really depends on the natural gas price. And with the low cost natural gas available to us here in Canada, let's say at 4 Canadian dollars a gigajoule of natural gas, we can really make hydrogen at very low cost of less than 2 Canadian dollars a kg of hydrogen, right? And this is with either SMR or ATR. But the key things to summarize from this slide here is, well, although blue hydrogen can make you very low cost hydrogen, blue hydrogen will require the geology for permanent CO2 storage. So really, you need to see if you have the right geology nearby. And it must be done at scale at very large centralized facilities for these costs to drop, right? And this is all talking about cost of hydrogen production. What about the carbon intensity of production? So when I talk about GHG intensity of hydrogen production, the first graph I have here is showing you carbon intensity of, say, hydrogen produced from water electrolysis. Like the cost, everything is dictated by the carbon intensity of your electricity source. So depending on the carbon intensity of your electricity, it will determine the carbon intensity of the hydrogen produced. In provinces like Ontario, BC, Quebec, where we have low carbon electricity grid, we can really make green hydrogen with very low carbon intensity, right? But in certain provinces, and I can highlight in Alberta where we're sitting right now, where we don't have a clean electricity grid at the moment, producing hydrogen while using the electricity from the grid will result in very, very high carbon intensity of the hydrogen produced, probably even worse than doing gray hydrogen, right? And what about blue hydrogen? Now, the graph I have here, again, a very busy chart, but I'll try and break it up for you. It's basically life cycle GHG intensity of your carbon, of your hydrogen, which is kilogram of CO2 per kg of hydrogen, as a function of two different things. So what I have in the chart here is basically carbon capture rates as 0%, 80%, and 94%. So 0% basically means gray hydrogen, and different percentages of carbon capture rates that are possible today. But what I also have is upstream methane emissions. So at methane leakage rates of 3% all the way to 0.5%, I have plotted the GHG intensity. So stoichiometrically speaking, when you make hydrogen from natural gas reforming, you make about 9 kg of CO2 for every kg of hydrogen, right? If you add upstream methane emissions, depending on the methane leakage rates you might assume, you can have a carbon intensity of hydrogen anywhere between 10 to 13 kgs of CO2 per kg of hydrogen. If you couple that with CCS, now you can really drop down the carbon intensity of blue hydrogen, but again, very sensitive to upstream methane emissions. So the key message again here is we must address climate change. Therefore, we must focus not only the technology for carbon capture and storage, but we must also address the upstream emissions from methane extraction and transport to your facility for making hydrogen. All right. So this is really laying out all the background work on what hydrogen production costs and what the intensity of carbon intensity of hydrogen produced will be. Let's talk about specifically supporting the hydrogen DRI facility in the Hamilton region, right? So like I said at the start of my talk, we're really looking at the Hamilton region, the Dofasco plant, which is basically transitioning to this 2.5 million tons of DRI facility. And due to the availability of public data, what we have assumed in our analysis is the mid-REX process. And when you talk about 2.5 million tons of DRI, the estimated demand to make this much direct reduced iron is about 492 tons of hydrogen per day. Okay, that's a number I like to stick in your heads, 492 tons of hydrogen per day. What does that mean? When I talk about 492 tons of hydrogen per day, that's 6% of all hydrogen produced in Canada today. As an used primarily as an industrial feedstock, right? But what if I have to make all of this hydrogen via water electrolysis or green hydrogen. To produce all of this hydrogen via electrolysis, we will require 27 gigawatt hour of electricity per day. 27 gigawatt hour of electricity per day. That's 6.5% of all the province's electricity generation, Ontario's electricity generation, which was about 153 terawatt hours per year. Now, even if you talk about cost, which we highlighted earlier as well, if you have electricity delivered at $126 per megawatt hour, you're talking about the cost of hydrogen produced at $53 a gigajoule, which is 10 times the cost of natural gas. Really not economically feasible. The scale and the cost of hydrogen produced from water electrolysis tells us this, that it is difficult to see how green hydrogen produced at the Dofasco site could be a cost-effective solution in the near future. And I'd like to stress on that, in the near future. We do think that green hydrogen will definitely play a role in the long-term scenario, but in the near future, it is difficult to see how green hydrogen can support all of that hydrogen demand by that DRI facility. So what about blue hydrogen? Now, once I talk about blue hydrogen, I need to talk about CCS, right? The carbon storage potential in that region. So how much CCS potential do we need? At 492 tons of hydrogen per day, we're talking about sequestering about 1.6 million tons of CO2 per year, right? Now that's significant, but that's great, because even to make CCS work, we need to work at those capacities to really drive down the cost. Now, when I talk about CO2 storage potential, Ontario has some potential in Southern Ontario, but there will be some competition for this pore space. Most of the CO2 storage potential for us in Eastern Canada is actually across the border in the United States, in neighboring states of Ohio, Pennsylvania, and Michigan. I have a table here which basically summarizes the potential CO2 storage potential in these regions. So what we did in this study is potentially look at producing hydrogen in these areas across the border in these states, which is about a 400-kilometer distance from Hamilton, and can we pipeline all of that hydrogen to the Hamilton region, right? These areas also have availability of low-cost natural gas, so the feedstock cost for making hydrogen should also be lower, right? So how do we deliver all of that hydrogen to the Hamilton region, right? I have here two graphs. The first graph on the top is basically hydrogen pipelining costs. What would it take, or what would be the cost of pipelining all of that hydrogen to the Hamilton region, which is 400 kilometers from there, right? In principle, we can pipeline hydrogen anywhere between 1 to 1.6 Canadian dollars of hydrogen, depending on the capacity utilization factor of the pipeline itself. At full utilization, we can drive down the cost of about 1 Canadian dollars a kg of hydrogen. And if I take this chart and I add all of the value chain or the supply chain cost to it, which is basically the cost of production, the cost of capturing CO2, the sequestering CO2, the hydrogen pipeline, what we're looking at anywhere between 3 to 4 Canadian dollars. This is delivered cost to the plant, right? And once I talk about even about 492 tons, if we optimize the cost for 492 tons of hydrogen per day, we're still looking at 3 Canadian dollars a kg of hydrogen, which is 4 times the natural gas cost. Because 3 Canadian dollars per kg of hydrogen is about $22 a gigajoule, which is 4 times the natural gas cost. So it's still significant, still much higher than your natural gas as an energy source. And other challenges here is that with a dedicated 400-kilometer pipeline, only feeding one company, only feeding one plant has a higher risk that could drive up costs and reduce project viability, and is also less likely to attract public support. So the next question that comes to mind, and this is all a systems level approach of thinking of how this net zero transition needs to happen, we need to ask ourselves the questions, are there other potential markets for low carbon hydrogen apart from the steel sector that could help reduce the cost while addressing climate change for Ontario and for Canada in general, right? So what we set out to do next is look at the potential role of hydrogen in the larger Ontario hydrogen economy, right? So when I talk about Ontario, the pie chart I have here is basically secondary energy demand. In Ontario, this is 2019 numbers. These numbers are basically from the Comprehensive Energy Use Database in Canada. Different sectors, so the total energy use was about 2,651 petajoules per year. They're divided into different sectors, transportation and buildings being the main consumers of all of the energy, followed by industry and agriculture, right? And once we look at these different sectors, the next task for us is to identify the most credible net zero solutions for these sectors, because I need to remind you, we basically power all of these sectors using carbon-based fuels coming from fossil fuels that has really driven the standard of living that we enjoy today. But if you're talking about a net zero solution, we'll have to replace these carbon-based fuels with net zero fuels such as electricity, such as hydrogen or biofuels, right? So I'll show you an example what we did for the transportation sector. We don't have time to go cover everything, but I'll talk about the transportation sector. So transportation sector 2019, majority of transportation energy use is coming from light duty vehicles, followed by heavy duty vehicles, air and other sectors. The next thing what we do is identify credible net zero options to replace current carbon fuels in these different sectors. So for example, light duty vehicles, we expect majority of light duty vehicles to be electrified in the future. Similarly, for medium duty vehicles, also majority of medium duty vehicles will be electrified with the use of battery electric vehicles. However, heavy duty vehicles, we potentially see a much bigger role for hydrogen for heavy duty transport, right? Now, once you put all of these things together, what you can calculate is the actual energy demand in the net zero future, right? And because a lot of these solutions, when we talk about battery electric vehicles or hydrogen fuel cell electric vehicles, these are much more energy efficient than current internal combustion engines. Therefore, all of that transition will result in efficiency improvement. So in a net zero future, the total energy requirement will be lower than what we use today. And we can do this for different sectors. So here we've done the same thing for agriculture. And what I'll try and do now is summarize things. So what we can do is calculate additional demand of these net zero fuels in 2050, right? This is all based on 2019 numbers. In transportation sector, we'll need an additional 33.9 terawatt hours of low carbon electricity, 102 petajoules of biofuels, 3,647 tons of hydrogen per day to really drive this net zero future. And we can do this for different sectors such as transportation, agriculture. We've also done it for buildings, basically for space heating in commercial and residential buildings, but also for industry. And what I'll go straight to is this summary. So I'll take a couple of seconds and just try and summarize what we have here. So I have a table here. On the left-hand side, I have 2019 energy use, which is energy, how do we use it today? And the right-hand side, all the numbers here is a net zero future, which basically will use electricity, hydrogen, and biofuels as zero emission energy carriers. Three numbers I want to highlight here before I get to my main point. The first key number, a net zero transition means we will have to double our public electricity grid from 138 terawatt hour of electricity use to 287. We will also require significant use of biofuels and significant CCS to really drive this net zero transition. And remember, all of these numbers are based on 2019 numbers. We have not accommodated for the population increase by 2050, which will further increase these numbers. But the most important one I want to get your attention to is the potential hydrogen demand to really drive the decarbonization of these different sectors. We're looking at potential demand of low carbon hydrogen of up to 12,000 tons of hydrogen per day. And this is just Ontario. This is not Canada-wide numbers. We're talking about Ontario as a province, right? And 12,000 tons of hydrogen is significant, but it's also what we need to drive down delivered cost, right? So remember, how do we talk about this? I talked about steel sector, but also the larger Ontario economy. Can we really drive down the delivered cost to the steel sector, right? So if you're also delivering large volumes of hydrogen, which also caters other sectors, you can decrease the pipeline cost. It can be almost a 50% reduction in the delivered cost by the pipeline. And also the overall delivered cost of hydrogen, you can decrease it to about 2.5 Canadian dollars a kg of hydrogen when you transport large volumes. So economies of scale really dictate all of these decrease in cost. So what does 2.5 Canadian dollars a kg of hydrogen mean for the steel sector? Let's look at that. And this is really wrapping up things. And this is one of the last slides I have for you. What would 2.5 Canadian dollars a kg of hydrogen mean? in this transition of natural gas DRI to hydrogen DRI facility. The top two graphs, I've already talked about it, the energy demand and the potential scope and GHG emissions from these different routes. At 2.5 Canadian dollars, we're looking at an increase of fuel cost by about $112 to $121 per ton of steel, from going from natural gas DRI to hydrogen DRI, right? If you take those numbers and really divide by them by your scope 1 emissions, what you really get, and this is the number I want to highlight here, is the CO2 abatement cost, which could be in the range of $200 to $360 per ton of CO2. So despite those low cost of hydrogen, we're still looking at CO2 abatement costs in this region, which, although looks high, is not too far. In 2030, we know our carbon taxes are about, announced carbon taxes are about $170 per ton of CO2, right? All right, so let's try and wrap up things and whatever we've talked about in terms of recommendations that came out from our analysis. The first thing I want to highlight here is the steel sector should look at reinvesting revenue from carbon pricing to decarbonize steelmaking and should work very closely with the government to do so. We should keep an eye out for new and monitor the progress of new innovations, such as methane pyrolysis to make hydrogen, right? Low GHG hydrogen production. This is what could be a breakthrough. We should work together with the government to build a premium market for low GHG steel. But the two most important ones that really come out from our analysis is really you need to drive economies of scale, and therefore the steel sector should also work. It's not really about only decarbonizing the steel sector, but we should work with the province and the federal government to really develop a regional strategy around hydrogen. And also work together with our neighbors in the US and understand the impact of the policies and different incentives announced across the border, which will affect low GHG hydrogen production. And on that note, really working with our neighbors, I'd like to bring to you this slide. I'm sure many of you on the call today has seen this announcement that basically came out a couple of weeks after we came out with our report. US has announced about $7 billion in funding for hydrogen hubs, right? Some of the hubs that I have highlighted here on the map is the Pacific Northwest Hydrogen Hub, the California Hub, and the others. What I want your attention to is these two hubs, which is really relevant for the steel sector in Ontario, Southern Ontario, which is the Midwest Hydrogen Hub and Appalachian Hydrogen Hub highlighted in the yellow here, right? These hubs, like I showed you at the start, have the geology for sequestering CO2, could also support the Ontario's demand for hydrogen in the future. And the announcements, the current announcement, although it's still developing as we move along, really these hubs are actually looking to produce low-cost blue hydrogen, which is basically natural gas plus CCS, right? And that's something we need to work on a framework where we work together with our neighbors to develop regional strategies around the use of hydrogen, right? And I think with that message, I really would like to wrap it up and conclude. Thank you so much for your attention. And please, if you have any questions, I'll be happy to answer them. Thank you so much.
Adnan, thank you for the presentation. That was great. Every time I review the report or listen to one of your presentations on the report, I'm often reminded not only of the opportunity hydrogen has with respect to integration in the steel sector, but also some of the material challenges to seeing the proliferation of the technology, whether it's to do with availability or cost, or technical feasibility in certain applications, right? There's a number of challenges on the table here that the report identifies and addresses. You know, I have a few questions in the hopper that I would like to ask. And the first area of focus was really on the economic impact and looking at the questions and answer or questions posed by the audience here. That's also a key focus of folks on the line. So maybe we can kind of hone in on that aspect of the report and your presentation first, really looking at how, you know, I think folks on the call would appreciate your perspective, succinct perspective on how the shift to hydrogen can impact overall steel production costs. Looking at some of the questions posed in the chat, maybe I'll read one off verbatim. So, considering the energy intensive nature of steel production, how efficient and economically viable is the utilization of hydrogen in steel production, taking into account hydrogen low volumetric energy density? And maybe, if you can approach that question both from the green hydrogen side of the equation and also the blue hydrogen side, that'd be fantastic.
Right. Thank you, David, for the question. And I think it's a very, very good question in that sense. So when we talk about the potential role of hydrogen for decarbonizing steel, the first point I really like to highlight here, and steel is a little different and it has its unique challenges to other sectors, right? When we talk about the use of hydrogen, we're not only talking about the use of hydrogen as an energy source or energy carrier, but we're also talking about using hydrogen as a reducing agent. And that's what we need to keep in mind. The real challenge for primary steel making, right now we use basically coal or coke as your reducing agent. So carbon is really used to reduce your iron ore. So we still need that reducing agent, right? So the potential for hydrogen, using hydrogen as an energy source, and like I highlighted in the presentation, the numbers tells us that has the best potential for reducing GHG emissions when we talk about Scope 1 emissions. The key challenge for our hydrogen is, can we deliver hydrogen at scale? Scale is the first thing I want to highlight here. When we talk about steel, one single integrated steelmaking facilities requires hundreds of tons of hydrogen per day, right? We also need to deliver it at a very low cost, which is really the entire presentation I was talking about. If you can sort that out, and I think not just Canada, globally, the steel sectors in different countries and different regions are really looking at hydrogen DRI as a potential possibility. That does not discount for other decarbonization routes. We also need to look at CCS, but like I highlighted in the start of the study, really our focus was mainly looking at, but we'll have to look at other options for decarbonizing steel as we move along.
That's great. And maybe just drilling down, there's another question in the chat here, focusing in on the economic side of this. And the question is focused on what is the break-even point for carbon intensity of the electricity supply, where green hydrogen beats blue hydrogen in greenhouse gas intensity of hydrogen production?
That's a very good question. Again, that depends on two things. So on the green hydrogen front, it depends on the carbon intensity of your hydrogen. On the blue hydrogen, you really have to look at not only the carbon capture rates you can get to, we're looking at about 80%, 90% capture rates, but we'll also look at upstream methane emissions, right? So both of these factors have to be put together to really come up with that break-even point. It's really about what you think really is. But like I said, on both aspects, in Canada today, we can immediately make low carbon hydrogen via water electrolysis, but also via blue hydrogen. We are blessed with natural resources. Our current carbon intensity of our electrical grids in many provinces, let me say, is very low, such as BC, such as Ontario, such as Quebec, which gives us a possibility. But the entire challenge with this net zero transition is not just the carbon intensity of electricity grid, the scale of electricity required, right? That's also something we need to keep in mind, the feasibility, where do we get that low carbon electricity from? So that's how I frame the answer. But again, with both technologies today, on the blue hydrogen front, let me also add, is we are looking, where does the right geology for CO2 sequestration lie? In Alberta, we have identified potential for CO2 sequestration, some of the best potential in the world, not just in the region, but in the world. But in Southern Ontario, the challenge is different. So whenever we talk about credible solutions for this net zero transition, we'll have to sit down and look at different areas, different sectors, different jurisdictions to really identify solutions. There is no one solution that works for all, right?
Yep. Great point. And maybe on that note, one of the last slides in your presentation was focusing in on regional developments in the United States. You mentioned Canada's standing with respect to natural resources globally. I'm wondering if you can comment on Canada's leadership position in the hydrogen space. Where are we in terms of, leading the pack? What can we learn from other jurisdictions, both maybe in terms of policy or in terms of technical implementation? I just kind of appreciate your insights on that one.
David, I think when I talk about the Canadian steel sector, we've already taken, measures over the last few years, as I showed in my introduction slides, to really reduce emissions from steel making over the last many years. But I think the path forward, and I think you're best placed in really to talk about that, what's going on in Canadian steel sector. So maybe what I'll do is actually flip that question to you, and maybe you can address of what's happening in the Canadian steel sector and what we're looking at.
Yeah, maybe I'll briefly comment. I was at COP28 recently, and hydrogen and a number of other decarbonization technologies were quickly discussed, or were at length discussed, I should say, in a number of different forums. And one of the common threads in a lot of these discussions, both at the technical and ministerial level, is that there are barriers to implementation that countries, including Canada, are facing that are identified in this report. So it was actually kind of reaffirming to see that issues with availability and cost are kind of across the board with potential implementation of hydrogen solutions in steelmaking and other sectors as well. I think where Canada can kind of, as you've identified, really punch above its weight is utilizing existing natural resources to really pull ahead of the pack and leverage its potential for blue hydrogen in particular, while also advancing technologies and cost competitiveness with green hydrogen. I think that, from my perspective, limited though it may be, is where Canada can kind of continue to shine. So just looking at some of the questions here, we have a more technical question in the Q&A. In a DRI process that already is utilizing natural gas, would it be more efficient to capture the CO2 emissions from the DRI process rather than capture the carbon in the process of making hydrogen, which would then be used in the DRI process? Any thoughts on that one?
It's an excellent question. And I think that's actually, I can even talk about that's an ongoing study in my group. I have a couple of students probably in the audience right now. That's what we're looking at. That needs to be also analyzed. That was really not considered, like I mentioned, in the context of the study and the objectives, the potential of capturing the CO2 from a natural gas DRI facility. But what I really need to highlight here, apart from the technical challenges and the cost, is really for Southern Ontario and for the Canadian steel sector is that availability of pore space and the competition for that pore space, right? Now, again, that's another thing what we need to do as a sector, but also we need to come out with more credible numbers about the potential for CO2 storage in that region, right? Once we can identify, I think then we can develop these strategic plans of what would be the possible solutions for decarbonization, decarbonizing different sectors, right? And the last point of what I can also add to that is, whenever we think about these transitions, always we need, I think, what I've learned over the last few years, you need to take a step back and have a very systems level approach and not just think about steel sector, which was really the last part of my presentation, is the potential use of low carbon hydrogen could have far-reaching implications for Ontario and for Canada in general, right? And not just Canada, many jurisdictions around the world have identified low-carbon hydrogen to play a key role in this net zero future. So I think those are the kind of thinkings and systems-level thinking that we need to keep in mind when we look at these, when we discuss these possible solutions.
That's great. And one area of the report and your presentation today focused in on kind of logistics costs, right? And we have another great question from the audience here, asking, is there a significant potential benefit to economic viability to co-locating hydrogen production with steel production, whether it's green or blue? Any thoughts on that? And does the report kind of speak to that specifically?
Well, that's again a very good question about co-locating. Really, it's about, when we talk about, especially when we identified at the start that we really see challenges with delivering that much amount of hydrogen with green hydrogen, right? So we're really looking at, in the short-term scenario, those skills, the potential of blue hydrogen. That's what we've analyzed in the study, basically. Now, it all depends. It all depends on the availability and where you see two sequestration sites are, And we also, although, I'm talking about building a hydrogen pipeline, but we all know in the audience right now, building a pipeline takes time, right? There's also, it's very early in this piece. I think there will be the biggest hurdle. I think what I see when I work on hydrogen technologies a lot is around code standards and regulations. And we need to work the system really. We need to identify and really move forward with that to really break down the hurdles and move forward, right? We also have technical challenges with hydrogen pipeline, especially high pressure pipelines with embrittlement, but that's ongoing work. I honestly think we will have the right solutions for it when the time comes and when the demand is there to overcome those technical challenges. But the challenges are more in economics. The challenges are more on the code standards and regulations at this point of time.
And we have a follow-up question in the chat, focusing in on that in particular, right? What are the issues with leveraging Canada's existing pipeline network for hydrogen? You've mentioned, there's regulatory and legal issues, there's technical issues. What are the main barriers here that we should be focusing in on addressing?
Absolutely. So at the moment, with our current infrastructure, we have an intensive natural gas pipeline network throughout the country. So can we really leverage that? And that's not just us. A lot of our different countries and other jurisdictions are really thinking along those same lines, right? How do we, take advantage of current infrastructure? When I talk about pipelining hydrogen, and we have a report on the techno-economics of hydrogen pipelines that is part of a transition accelerator report, and I'd like everyone to encourage going through that as well, is when we talk about blending hydrogen into current natural gas, we know right now we can safely blend anywhere between 15 to 20 volume%. Higher, we're still looking at what would be the challenges of blending higher amounts of hydrogen. Pure hydrogen pipelines, embrittlement, I talked about embrittlement in my previous response, but it's really a challenge with high strength steel at high pressures. Low strength steel, not as much of a problem with embrittlement. But again, like I said, I'll repeat myself, the technical challenges with embrittlement and transporting larger volumes of hydrogen, I think can be overcome when we've been transporting hydrogen for a long time, right? In different industrial complexes, we know how to transport hydrogen in pipelines, not so much in high pressure transmission pipelines, but I think the solutions are there and we can come up with solutions when the time comes. But there are other challenges, and I'll probably shift the focus is not just about hydrogen, but the steel sector in Canada also will have other challenges. And maybe, David, you could also speak to the fact is how much of this shift from a hydrogen-based to a hydrogen-based steel production will affect Canada's position in an international steel market. And I think that's what we need to address and talk to the audience about as well. David, I think you're mute.
Okay, perfect. Thanks for catching that before I went on too long there. So, at a high level, over the past 10 years, Canada has seen its imports of steel rise from jurisdictions without any carbon framework, from high intensity steel producing nation, carbon intensity steel producing nations, rise from 20% to 40% of our domestic procurement. So it's doubled in the past 10 years. Meanwhile, our domestic steel companies, who are already among the lowest in terms of carbon intensity per ton of steel produced, leaders of green steel production, they are furthering their efforts to mitigate environmental impacts of their operations. So I think that there's a few things at play here. We have to continue to support domestic steel production as they transition to a low carbon economy, but we also have to protect the market and demand for green steel, and that can be through carbon border adjustment mechanisms. It can be through reciprocal trade policies. There's a number of different ways, public and private green procurement policies as well. There's a number of different ways to ensure that continued demand for green steel grows, and our domestic steel producers are protected against jurisdictions that, quite frankly, have little, if any, environmental regulatory environments governing their operations. So I think that it's the continued decarbonization of steel production in Canada and in other jurisdictions as well, has to be protected at the policy level,
Yes.
because these investments are costly. They're worthwhile in the end, most assuredly, but we're competing with jurisdictions that aren't playing by the same rules. So I think that's an important thing to note. Just looking at the time, maybe we'll wrap it up with one last question on a technical question about the impact of hydrogen on steel quality, and whether the use of hydrogen in steel production has any impact on the quality or properties of the final steel product compared to kind of traditional methods.
Right. So that's again a very important question. I should have addressed that during my presentation. When we talk about steel making, we need to remember what is steel. Steel is basically iron with a small amount of other elements, but one of the key ones is carbon, right? Which really gives you the strength in steel. So when we talk about using 100% pure hydrogen as an energy source, but also as a reducing agent, then we need to talk about where the carbon source will come from, right? So in that sense, and if you saw our analysis as well, we've introduced a small amount of natural gas to really provide that carbon source. But also for another important reasons, when we talk about reducing iron ore, the reduction of iron ore via hydrogen is an endothermic process. To really maintain that temperature in the shaft furnace, we need that extra thermal energy, which is also introduced by natural gas, introducing that small amount of natural gas. It could come from other carbon-based sources, such as biomass, which is also presented in the analysis, and that could really drive down. So that's important to note. And in that sense, if you can do that, there should be no compromise in the quality of steel you can produce.
Perfect. Well, I think we've reached the end of our time today. So Adnan, thank you again for your presentation and for the insightful conversation. Big thanks to the Transition Accelerator for their work on this report, as well as to Enercan for their financial partnership in supporting this research. And again, and of course, thanks to the Edmonton Region Hydrogen Hub for setting up today's discussion. So to wrap things up, I'll turn it back over to Professor Dave Layzell.
Thank you very much, David, and thank you, Adnan, for a very interesting and informative discussion. And thank you to everyone who's joined us for the conversation today. If you'd like to share a copy of this presentation with one of your colleagues, the recording of this webinar is going to be available on the Edmonton Regional Hydrogen Hub's website, that's erh2.ca, and on its YouTube channel within the next day or so. You can also find a hefty report available to describe all of the results of this. That'll be a really good cure for insomnia. And it'll be on the Transition Accelerator's website, www.transitionaccelerator.ca. Now, this is the final webinar of the year for the Edmonton Regional Hydrogen Hub, but please check on the erh2.ca website or on social media for announcements about some of the next year's programming. We're also excited to share details on a new course that the Transition Accelerator is launching on the use of clean fuels in heavy-duty transportation. The course is designed for transportation professionals looking to build an understanding of energy pathways for heavy-duty trucking fleets. And if you want to register your interest and be the first to know when this course dates are going to be announced, please follow the link in the chat, and there should be a link in the chat box that is being put in there now. I should make sure it's there. I think it is, but anyhow, it's in the chat there, and you can register for interest in the course and decide whether you'd like to take that. Thank you, everyone. Have a great day.